Hey, my name is Nathan West, and I chose to do my microkernel-based operating systems research on the operating system QNX. So this is going to be all about QNX. I chose it because in researching different microkernel operating systems, I found QNX fascinating because of how it's used as an embedded system in vehicles and some of the new stuff they're looking at doing with that. So that's kind of what directed me to QNX. So what is QNX? Well, it's a microkernel-based operating system with a real-time environment. It's been used in many systems where real-time performance, network, and development flexibility are important requirements. The microkernel can support various elective processes, which that means it can be scaled up or scaled down in the case of embedded systems. It has a wide variety of uses. Its real-time environment is critical for applications like in medical instruments, like I mentioned, embedded systems in cars, process controls, financial transactions. It has a wide variety of uses. QNX is currently owned by BlackBerry, and BlackBerry CEO John Chen described it as the crown jewel of the company. This is his quote. He says, QNX is probably one of the crown jewels. Every time our partners reach out to me, our customers tell me they really want to work on QNX with them. So it's been a major success for BlackBerry. And that's according to the article, BlackBerry's QNX, Why It's So Valuable. So some historical perspective of QNX. According to the QNX software development book set, a company called Quantum Software Systems Limited was founded in 1980. This was by two recent graduates of the University of Waterloo in Ontario, Canada. So originally the operating system was called QNX, but it was renamed QNX to avoid a Unix trademark. The first release was called QNX, and it was commercially a success, and it was followed by QNX version 2 in the mid-80s. There are still some mission-critical systems that are running QNX 2 today, and that's according to the developer's book set. In 1991, QNX 4 was released with POSIX support, and in 1995, QNX Neutrino was released, and that is currently BlackBerry's product. So what are the goals and purposes of QNX? Well, a microkernel-based operating system is designed to have a small kernel that provides finite services utilized by a set of optional cooperating processes. So the idea behind this is in order to enable the higher level functionality of the operating system, the microkernel does not include services like a file system. That's usually expected of an operating system. Instead, these services are provided by selected processes. The real ambition with that is to design a microkernel operating system that's not just small, but modular. Modularity is the real goal. It embodies a fundamental change in the design of operating systems. The microkernel provides IPC services that are utilized to cement the operating system. The service's performance and flexibility dictates the performance of the operating system. QNX microkernel is comparable to a real-time executive in terms of services provided and real-time performance, with a few exceptions. IP services are one of those exceptions. QNX differs from an executive by how the IP services are utilized to expand the functionality of the kernel, with service providing processes. The operating system is designed as a set of cooperating processes, and these are managed by the microkernel. User-written processes can extend the operating system's functionality in addition to serving industry-specific applications. The core operating system's fundamental reliability won't be affected by user-written extensions to its functionality. Issues real-time executives face while implementing the POSIX standard is that runtime environment is frequently a single process, multi-threaded model, and the memory between the threads is unprotected. QNX Neutrino, though, utilizes a memory management unit, at MMU. It's a hardware component that controls memory access to the CPU. And this component allows the QNX operating system to package the complete POSIX model in a secure environment. And this is according to the developer's book set. So as you can see, in conventional executives, and I have that here in Figure 1, they don't provide memory protection. All right. In a monolithic operating system, as seen in Figure 2, the system processes lack protection. But a microkernel operating system, like in Figure 3, these provide complete memory protection, and not only for user applications, but for the operating system components, such as file systems, device drivers, etc. And these 3 images were taken from the developer's book set. Now, QNX is a microkernel-based operating system. It offers modularity, and I think that's the big goal and the big takeaway. You add the processes you want, and you remove those that are unnecessary for your particular needs. It's comparable to a real-time executive. Utilizing memory management unit, it enables QNX to deliver the complete POSIX process model, guaranteeing a protected environment. These factors give QNX operating system flexibility and modularity. And that's why I believe you see it running in a wide variety of applications. So what standards and platforms govern QNX? So like I mentioned, it's governed by the POSIX standards. This is beneficial because based on my research, a recurring problem with real-time application development is that frequently companies will use their own proprietary API. Many companies utilize their own in-house operating systems. POSIX is an opportunity to provide industry standards and unify the marketplace. It essentially encompasses the base functionality of a Unix operating system. It defines the API for process management, file system input-output, device input-output, and basic IPC. It provides a standard for many applications. POSIX offers real-time extensions to the base standard. These extensions include prioritized process scheduling, high-resolution timer control, real-time extensions to signals, enhanced IPC, primitives, asynchronous and synchronous input-output, and real-time sequential file support. The real-time extensions also describe facilities such as attaching interrupt handlers. Pardon me. The POSIX environment can be further extended to include the creation and management of multiple threads of execution. And the POSIX standards includes application environment profiles such as real-time AEP, embedded systems AEP, and others for the POSIX environment. These support different sets of embedded features. And a lot of that information was gathered from the developer's book set. QNX can be found in a wide variety of platforms. The goals of the QNX Neutrino real-time operating system was to develop the POSIX API in a scalable form that will be suitable for a wide variety of platforms. So you have small embedded systems that have resource constraints, and you can even have high-end distributed computing environments. QNX supports multiple processor families such as x86 and ARM. QNX is readily scalable because it's a microkernel operating system, and we talked about the modularity. You can omit or add particular processes to remove or include additional functionality. This added flexibility means you can use a single microkernel operating system for a greater range of purposes than can be achieved with a real-time executive. When companies are considering product development, the scalability comes in handy. A line of products often provides greater functionality with each successive model. Developers who are not using a microkernel operating system, well, they might be forced to change operating systems to meet the demands for the new functionality in the latest version. But with a microkernel operating system, a developer can scale the system with new versions. So you have new functionality, well, you can add modular services. To include like networking, file systems, graphical user interfaces. And from version to version, the application code is portable because the operating system didn't change. So the tool used to change each version stays the same, The skill set of the developers stay in demand, and all these factors reduce time to market, and it saves companies money. So QNX is ideal for embedded systems, embedded platforms with real-time applications. It can be scaled as small as you might need it. It provides the basic elements of embedded real-time systems, such as fast context switching, priority-driven preemptive scheduling, threads, and multitasking. It does not forgo industrial standards to achieve such a small system because it delivers these capabilities with a POSIX standard API. Environments that require rigorous resource management and scheduling are ideal for QNX, which is a highly responsive operating system. So, how is QNX designed and implemented? So BlackBerry's QNX operating system has been developed from both ends of the computing spectrum, from high-end symmetrical multiprocessing machines to limited embedded systems. The design goals of QNX Neutrino has been to accommodate both sets of functionality. The QNX real-time operating system, it has a small microkernel, and it manages a group of cooperating processes, like we have here in Figure 4. The structure is less of a hierarchy and more of a team with multiple players of equal rank. They'll all interact with each other through the help of the coordinating kernel. Players can be added or removed to meet the needs of the system, whether it be a large or embedded system. So here you can see in my graphic, Figure 4, these might be the different players. And they may not be found in all solutions. It could be you don't need all of these, but that's where the modularity and flexibility comes in handy. The QNX microkernel directly provides most of the services for the real-time and the thread. No other operating systems are needed for those services. A lot of real-time executives and kernels lack a process model or a protected memory model and only offer non-memory protected threaded models. Full POSIX compliance cannot be achieved without a process model. The QNX operating system has direct support for threads, but to make this functionality work for processes that have multiple threads, it depends on its process manager. And a lot of the technical information for this research project, I relied on the developer book set directly from BlackBerry. So in the QNX Neutrino RTOS architecture, microkernels have little complexity. There's a cap on the kernel for the longest code that's not preemptible. Addressing complex multiprocessor issues, it's a tractable problem because of the small code size. To reduce the complexity of the microkernel, services were chosen on the basis of having a short execution path. External processes and threads are assigned work-intensive operations, so the amount of work required is trivial in comparison. Runtime overhead is split by reducing the functionality between the kernel and external processes. The simplified kernel can achieve very quick context switching times, and the QNX operating system relies on the microkernel's ability to support kernel calls. Calls such as threads, message passing, signals, clocks, timers, interrupt handlers, semaphores, mutual exclusion locks, condition variables, and barriers. And even while passing message between the process, the QNX operating system is fully preemptible and is able to resume the message pass where it left off before preemption. All right. So like we said, that small code size with a short execution path. And here in Figure 5, you can see how preemption would work. So when the system call makes entry, interrupts are turned off, and it's in a matter of microseconds. And then when the kernel processes an operation, This takes micro to milliseconds. Interrupts are on, and there is full preemption. Then you have lockdown, and during lockdown, there's no preemption, but the interrupts are still on. And then when it's exits, interrupts are off again. The benefit to this system is that preemption is prevented and interrupts are turned off for very short periods of time. All right, what are the subcomponents of QNX and their functions? So Process Manager in a QNX real-time operating system is paired with the microkernel. This is a single module referred to as proc_into. And I tried to look up how to pronounce that. I had trouble finding anything. It is responsible for process management, memory management, and path name management. So a message send function kernel call to proc_into from a user process allows the process to access the microkernel functions directly. And process management is proc_into's first responsibility. Dynamically creating new POSIX processes and possibly multiple POSIX threads. These new processes are dependent on memory management and path name management. These are proc_into's other responsibilities. POSIX model for virtual memory systems is implemented with the addition of some QNX extensions. Included among these extensions are virtual address space and mapping to memory objects. Manipulating mappings at page size and memory map files with persistent file systems backing storage. Demand pagings that are not allocated until reference, global page replacement algorithm, and copy on write sharing. And there's more examples. The memory manager's responsibilities are all virtually memory based and not physical memory. Virtual memory helps, like we've been learning in class, with safety and security. It gives a per process view and it allows for shared libraries and memory objects. The memory manager unit is hardware that controls CPU access to memory and enables QNX to follow POSIX standards. The memory management unit is turned on before the kernel itself early in the startup process, and once the memory management is running, there's no direct reference to physical memory. Instead, the MMU translates the virtual memory address into physical memory address. And the memory manager is responsible for mapping the virtual addresses to physical addresses and all other information related to managing physical addresses. Physical memory is divided up into fixed size pages, page frames. We talked about those in class. In QNX, they're typically 4 kilobytes of physical memory. Physical memory is also allocated for file systems. So you can see this in figure 6. Sorry, I made the figure a little small. But these are the divided up page frames, and you can see how in virtual memory they're mapped to physical memory. So the page frame divisions as shown in the figure. All right, the association between virtual and physical pages, found this interesting, is not fixed. A virtual page is backed. It's said to be backed by physical memory if it's associated with the physical page. Every process is assigned its own virtual memory address, and this should help prevent coding errors in a thread from one process doing damage to memory used by a thread from another process. All right, so RAM is divided up into zones of contiguous physical memory. This division is intended to reduce fragmentation by having dedicated zones for certain allocation types. The virtual address space of a process is divided into regions. These regions are a range of contiguous virtual addresses. There's an mmap function to create the maps. Faulting and paging on demand is the default behavior. A fault occurs the first time you access a newly created region from the mmap function. An association is made between a virtual page and a physical page by the memory manager. And physical pages are not always assigned to virtual pages, like I mentioned earlier. If a virtual page is not backed by the physical page, the memory manager finds one and a fault occurs. A fault occurs if more than one address space has a region that refers to the same virtual page. The memory manager will then allocate a new virtual page association with the physical page. It's the job of the memory manager to keep track of how much memory is required in order to back all the allocated memory. Memory can be unlocked, locked, or super locked. Unlocked memory is allowed to be paged in and paged out. The memory might be allocated when it's first mapped, but there's no entries in the page table for unlocked memory. If there's an attempt to access the memory, it will fail and the process will stay in the wait page state. The memory manager will then create a page table entries and initialize the memory. Locked memory, on the other hand, is not allowed to be paged in or paged out. In order to maintain statistics on uses and modifications, there will still be a page fault whenever it's accessed. Processes can be locked. Processes can lock or share overlapping regions, and it will remain locked until all the processes are finished with it. Now, super locked memory does not allow faulting. Memory must be initialized, privatized, and have a permission set immediately after it's mapped. And the whole address is considered super locked. All right, input and output resources, they're not included within the microkernel. These resources are started dynamically at runtime by resource manager processes. The Procting2 manager, like we mentioned, enables resource managers to administer a subset of path namespace. Procting2 is responsible for keeping track of all the resource managers and their domains of authority. So it maintains a path name tree, and it tells what processes own what portions of the path name. This approach to managed path namespace enables QNX to keep the POSIX standards for device and file access. These services are optional for embedded systems. Whenever a process requests a file, POSIX routine sends the path name to Procting2, and Procting2 compares the path name to a prefix tree. And that will help it determine which resource manager should receive the message. After opening an I/O resource, the open function returns a file descriptor. A file descriptor is presented by an integer, and it's used for all additional I/O requests to that resource manager. The file descriptor is local to each process, unlike the path namespace. So what that means is the file descriptor can be used in conjunction with a server connection ID to identify the control structure responsible for the call, the open call. QNX allows user-written processes to act like resource managers. This gives QNX a great degree of flexibility, like I was talking about earlier with the modularity. It reduces the runtime memory requirements. It allows QNX to support a wider variety of devices in custom embedded systems. The user-written processes can be started and stopped dynamically. The job of a resource manager is usually to provide an interface for all the different kinds of devices. This could include handling real hardware devices and virtual devices. This functionality is typically the responsibility of device drivers, but interestingly, in the case of QNX, it's the responsibility of the resource manager. And the resource manager is treated like any other user-level program. It essentially is a user-level program that handles messages from other programs, and it sometimes communicates with the hardware. In the QNX Neutrino real-time operating system, it makes it simple and it makes it flexible to develop drivers for new hardware, and that's crucial for embedded systems. The file systems of the QNX operating system, they offer an abundant variety of file systems. They operate outside of the kernel, and they're important for communication, messages between applications. The messages are generated from a shared library courtesy of the POSIX API. File systems behave like resource managers, and like resource managers, they control portions of the path namespace, and they provide file system services. Services like read, write, open, close, and seek. A portion of the path name is referred to as mount point, and I'll reference that several times as we go. File system resource managers control a mount point and structures below it. They also control access and authorization and permissions of the path name components. File systems can start and stop dynamically, and they run concurrently. A single unified path name can represent an application no matter the underlying configuration file system. QNX supports a few special file system types. For example, a pass-through file system. It's like a parent file system that can manipulate underlying child systems, file systems. And an example of this, of a pass-through system, would be an inflator file system, according to the developer's book set. Care has to be taken when running multiple pass-through file systems because this can lead to deadlocks. I find it interesting as I've done this research, making references back to what we're learning in class. And it's interesting that in this particular case, it increases the risk of deadlocks because you have multiple pass-through file systems. Now, a virtual file system is a file system where the underlying media is not tied directly to specific files or directories until it's needed on a demand basis. An example of a virtual file system would be the proc file system. I apologize, this slide. I crammed a lot into this slide. The QNX network service operates outside of the kernel. There's a single unified interface no matter the configuration. Network drivers can be dynamically started and stopped, and network protocols can run together in many different combinations, and that's useful because it increases the flexibility of QNX. The network subsystems have an active executable component called the IO-PKT. It loads protocol and drive modules depending on the configuration it's given in the command line or in the mount command. Multiple network protocols can be loaded on the fly because of this, the IO-PKT. It employs a zero-copy architecture. The IO-PKT component is similar to other component subsystems. Like other component subsystems, it has drivers at the bottom layer, and these pass data to and receive data from the hardware. The drivers provide a unified interface that allows them to direct packets and protocols such as TCP and UDP, like we learned about in our networking class. And these protocols are passed into protocol processing components in the stack. There is a resource manager in the QNX that acts as a go-between for the stack and user applications, and it communicates with networking applications using a message stream. It provides a standard interface. So what are the pros and cons of QNX? And I've already been addressing a lot of the pros as we've been going. So QNX, the pros are the pros of the microkernel in the real-time operating system. The microkernel gives QNX modularity and a lot of flexibility. This makes it suitable for a variety of environments. Embedded systems in particular, because you can remove functionality to make it as small and focused as it needs to be, minimizing the size of the operating system and by excluding everything you don't need. And the modularity, like we discussed earlier, it allows developers to add functionality down the line as features grow or if the environment changes and changes need to be made. Developers don't have to make changes in the operating system when new versions are created, and QNX implements the POSIX standards. This encourages developers and companies to use QNX because it follows into industry standards. And that means it will fit in with other systems that follow those standards, pre-existing systems. Developers with a background in POSIX will be comfortable and familiar with the functionality of the QNX operating system. Now, disadvantages. I would say the biggest disadvantages of the QNX operating system, BlackBerry owns it, and a paid-for license is required to use it. Also, it became closed source whenever BlackBerry bought it. Before, it was open source, and there was a lot more community support for QNX. Now it's limited because of its closed source nature. So one disadvantage of the POSIX standard is it limits customization because it has to adhere to the standards. So for certain applications, that will be considered a different disadvantage. And I gathered some of that information from the article that was comparing Linux and QNX, called Differences Between Linux and QNX. So what companies are currently involved in this line of business? Well, BlackBerry, like I've said, owns and licensed the QNX Neutrino operating system. Lots of other companies utilize it, though. The operating system is popular with embedded products, but that's just one of the areas that it's seen a lot of success. In particular, embedded systems in automobiles, the automotive industry. According to Jordan Golson of Tech Republic, BlackBerry QNX is the standard for automobile embedded operating systems. And that has a lot to do with the fact that it comes pre-certified to automotive industry standards. And that's very important to automotive manufacturers because of the dangerous nature of cars. With the introduction of new software-based safety features in cars, it's really imperative that the operating system works as expected and as intended. New cars can include features for like emergency braking, blind spot awareness, lane assistance, advanced cruise control features, and it's really important that those things work as expected and don't malfunction. There are stories out there of a car's operating system malfunctioning and there being a resulting crash. You'll hear that with like Tesla. Like if it's pedestrian or stopped vehicle detection software doesn't work, it might ram into a stalled vehicle. There's been a few stories out there like that. Some more examples of how this could go wrong. Like back in 2015, hackers remotely manipulated Jeep's operating system, and they were able to make changes to like the windshield wiper, climate control, and the radio. And that's according to the article BlackBerry has built. And that's pretty harmless, 2015, but you can see how down the line, when cars rely more on their operating system for things like driverless cars, that could be much more dangerous. So as these features expand, drivers rely on them more, the potential for failure or interference increases, and so do the consequences. To give you a recent example, Hyundai and Kia, they've garnered a lot of attention because of how easy it is to steal their cars. There are some insurance companies that won't insure their cars, and it's because they lack a feature called an immobilizer. An immobilizer works by communicating between a key fob and a car's engine control unit. If the code between them doesn't match, the engine won't start. Because Kia and Hyundai lack that, there's been a popular trend on TikTok to steal those videos for clout. And supposedly it affects up to 3.8 million Hyundai and 4.5 million Kia. Now, both these companies have released new deterrent software, and that kind of shows you how QNX's flexibility comes into play, because you may need to add functionality like Hyundai and Kia have because of how easy it was to steal their car. They had to push out software because if they didn't, that would be some major recalls that would affect a lot of vehicles. This all adds value to QNX's pre-certification of automotive and industry standards. According to Jordan Golson of Tech Republic, this is why Volvo chose to use QNX embedded systems in their vehicle. It's also why 23 out of 25 major electric vehicle manufacturers are choosing QNX. It saves car manufacturers from having to duplicate the work at their own expense. So a car's operating system, it doesn't really differentiate it competitively from manufacturer to manufacturer. So if I'm considering between a Ford and a Dodge, I'm not really asking myself what the underlying operating system is. So, according to Brian of Auto Connected Car News, BlackBerry's QNX operating system, it's embedded in 215 million vehicles as of 2022. And that's the figure that I have here, figure 7. And you can see how quickly BlackBerry has taken over the embedded vehicle sector. Over the course of less than a decade, it's seen its market share grow over 1,000%. And QNX serves the biggest car manufacturers, from Toyota and Honda to BMW. BlackBerry's operating system, it doesn't just handle important safety features, vehicle operation, it handles a car's media player. According to Larry Deegan of ZDNet, BlackBerry has a lucrative relationship with Apple. Apple's CarPlay, which is a very desirable feature. I actually chose my car partially because it included it. It runs on top of QNX. And Apple has cultivated this relationship with BlackBerry to ensure that its iOS is in cars. So if I'm considering, a car's operating system, I'm not thinking of QNX. I'm thinking of what rides on top. Does it support Apple CarPlay, or does it support Android? What does the car support? And so QNX doesn't really come into play because those operating systems ride on top of QNX. Now, it's not just popular in vehicles, which is mainly what I focus my research on, but it's also effective in medical devices, where real-time environment is crucial. I read an article by Zukan Lee, I think you pronounce his name. It's called The Design of Heartbeat Monitoring Based on Serial Port and Its Implementation in QNX. QNX is used in a heartbeat monitor to send, receive, and process heartbeat information. And this information is needed to be coordinated by timers, which are realized by the QNX operating system. And so it's utilized in a lot of medical devices, like heartbeat monitors. What is the future trend of QNX? And this is what really got me excited. QNX has an exciting future, and it has a lot of potential for growth. I'm especially interested in the automotive industry. It's looking at big shakeups in the following decade, and that's going to decide many winners and losers. And QNX, as we've seen, being in 23 out of 25 electric vehicle manufacturers, is supposed to be a winner. According to the article, BlackBerry has built the iOS of cars. It controls 68% of global electric vehicle operating system market. So 68% of electric vehicles. An exception would be Tesla. BlackBerry's also partnered with Amazon to introduce cloud connectivity to cars, so that they can keep track of things like vehicle health. And cloud connectivity is important for another upcoming cool feature, which is automated driving or driver assist. And so this partnership with Amazon has a focus on advanced driver assist programs. And QNX operating system is also playing an important role in LiDAR sensors. According to the article, Innoviz selects BlackBerry QNX. LiDAR sensors are an important component because they're used for safety critical embedded systems for detection. So all of these articles state that QNX platform is good for these systems because it's agile and it's a strong foundation for developers. And it's got that reputation of being safe because of meeting industry standards. So Innoviz, it's considered a leader focused on safe future autonomous vehicles using their LiDAR technology. And it's found throughout the company has a presence in US and in European and Asian car markets. And it's not the only company that QNX is working with a LiDAR technology. LeaderTech also chose BlackBerry operating system for their LiDAR sensors. All right. And to summarize, the QNX microkernel real-time operating system, it has a very interesting future. its future readiness and survivability thus far owes itself to its flexibility and modularity, and that's all because of the fact that it's a microkernel. The environment for technology advancement has always been rapid and sometimes unpredictable. And a microkernel operating system is suitable for this kind of environment because functionality can be added or removed, that modularity. Car manufacturers in particular seem to value QNX. The benefits being it lies underneath their own system. It does not physically take credit for the important role it plays. So there's really not a reason for car companies to develop their own in-house operating system, because it's not going to distinguish them competitively in consumers' decision on which car they buy. So for these reasons, I think we can expect QNX to be in the operating system of our vehicles for many years to come. And I'm especially excited to see what it does with automated driving and all the safety features. In my car, I have braking assist and lane assist, and I find those to be extremely helpful. So I'm excited to see how QNX is used in the future. Here's my references. Like I said earlier, I relied heavily for the technical aspects on the book set that QNX offers for software development. And then using the school's library, I located a lot of interesting articles, like the one on the design of a heartbeat monitoring monitor, and also the articles on LiDAR sensors. So thank you for taking time to listen to my presentation. It's been a fascinating project, and I'm really excited by what I was able to learn from it. Thanks.